Okay, ready? Yeah, you want me to do the pose? Okay, so we're going to move on to a plane. Everyone remembers what we needed to find the equation of a line?
A pointing vector, direction vector.
Pointing direction vector. Where should the direction vector be pointing? Parallel to the line. Okay, so in a similar way for a plane, we're also going to need to find a point and a vector in order to determine its equation. However, a parallel direction is not going to work, right? Why is that?
Because it would be on the plane, right?
Yeah. So why is that a problem?
You would have infinitely many.
Infinitely many, right? There's never going to be a way to narrow them down, right? So let's say this thing here is a plane. How many directions are parallel to this plane, right? Let's say this chalk is a vector. That, right? If you define it in terms of parallel, you'll never be able to actually nail down a direction, right? So what direction is the best one to use? Orthogonal, right? Turns out that if you have a plane, that's the only way to be orthogonal, right? Well, that and it's negative, but basically that's the same one thing, right? There's a one way to be orthogonal to a plane, infinite ways to be parallel to the plane. So it turns out to find the equation of a plane, we need a point and a vector, but this time the vector is not parallel to the plane, it has to be orthogonal, right? And so how do we get to that? There it is, you have a plane. This is a vector, we're going to call it n. This is the vector orthogonal to the plane. I label it by n because it's actually called a normal vector. Right? So an orthogonal vector to a plane is called a normal vector to the plane. Right? So it will actually intersect the plane at a right angle. Now, in the same way that we did the line where we're setting up things in terms of position vectors, we can do the same thing here. Let's say I want my initial point to be here, which is R0, which I could let be x0, y0, z0. Right? So I have a vector hitting that point. And then here's some other point, the arbitrary point on the line, on the plane, x, y, z, vector hitting that point. So what do I know about the normal vector? Well, the normal vector is orthogonal to, of course, the vector connecting those 2 points, right? So what does that mean? So 2 points on the plane, I can connect them with a vector. The normal vector obviously has to be orthogonal to that vector, right? When I connect the 2 points on the plane. What does that mean?
The cross product is 0.
No.
No.
Cross product is 0 means what?
Parallel.
Parallel.
So the dot product.
Dot product has to be 0. It means if I take the dot product of n dotted with the vector r minus r0, I would actually get, the dot product is a scalar, I would actually get the scalar 0. Right? Now if r is x, y, z, and this is x naught, y naught, z naught, then this means it's conventional to call n ABC, not to be confused with the ABC from the line. And R is x, y, z. R0 is x0, y0, z0. Then what we'd actually get is ABC dot product with the vector x minus x0, y minus y0, z minus z0. and that should equal to 0. Well, we can actually simplify that by the dot product formula. This gives us a times x minus x0. I'm going to write on the board, the other board, bigger, because it's a big deal for your class. And there we have it. This that actually gives us the equation of a plane, right? Now your A, B, and C in general, and your x naught, y naught, z naught in general, remember these are in general constants, right? So, example, if I write 2x minus 1 plus 3, 5 plus 3 plus z equals 0 is a plane, right? And I can simplify this if I want, or anything else. And x plus y plus 2z equals 4 is also a plane, right? Things that look like this. Notice that if you left the z out of the equation, it just looks like a straight line in R2, right? So this is very important that you actually don't confuse these guys. These are actually planes. If you see x plus y equals 4, it's not a line anymore. That was way back in calc 2. It's a plane now, right? So this is actually the equation of a plane. That's what they look like. It looks like a linear combination of the x, y, and z, right? And this is a plane in R3, right? That's the general formula. And what do you need? You need a normal vector, which is a vector orthogonal to the plane, and a point in the plane x naught, y naught, z naught. Yes?
How would that give you a normal vector that's orthogonal to the plane? That would be perpendicular to that vector, right?
Yeah.
But it wouldn't, how do you know it's not tilted on a plane?
No, that's more of a conceptual thing, right? We're assuming if we could find a vector that's normal to the plane, then it would be perpendicular to every vector in the plane, right?
Oh.
So I just picked a random vector in the plane, right? I just found 2 points in the plane and made a vector out of it. If the normal vector is perpendicular, it's definitely perpendicular to that vector.
Yeah.
It would be perpendicular to everything, every vector in the plane, right?
Okay.
So this is just a conceptual setup. Of course, we will be able to determine what vectors that are normal to the plane, where this would work, right? But this is saying, assuming we could find it, this is what would happen, right? And this would be the equation we end up with, and it will turn out that we will be able to find it if we're given enough information. So. Just want to write this down. What do we need for a line?
A point and a direction vector.
Right? So what do we need for a line? Point and direction vector. For a line, we need a point and a direction vector. What do we need for a line?
A point and a direction vector.
What do we need for a plane?
A point and a normal vector.
equations for the line. R equals R0 plus VT. This is called the vector form. You could also write this as, if you want to flesh it out, which sometimes it's useful, x0, y0, z0 plus t times a plus c. Also the vector form. You could have it in symmetric form, x equals x naught plus at, y equals y naught plus bt. That equals z naught plus ct. This is called the parametric form. Solve for the t, x over x naught over a equals y minus y naught over b. Equals z minus z naught over c. This is the symmetric form. Right? So what do we need for a line? Pointing and direction vector. These are the possible equations you can write it down in. Right? The direction vector is the ABC. The point is x naught, y naught, z naught. This guy, our equation, is just a times x minus x naught plus b times y minus y naught plus. So if I ask you on a test or a quiz or something like that, what does the equation plane looks like and what do the pieces mean? I expect you to be able to write this down, right? I expect you to also remember this. And it looks very simple and you might be wondering why I'm writing it down, because you're really going to have to fix this in your brain. Because they're going to give you word problems and they're going to tell you, oh, lines are over here and planes are over there, and what if this line intersects with that plane and this plane intersects with that line, find this line of intersection. And then it's going to get all confusing, but you just need to remember, what are you looking for? No matter what they tell me, I just need to find a point and a direction. I just need to find what is a point on my line, what direction is it moving, right? And you need to just, buckle down and stay focused and don't let things confuse you. And it helps to go back to basics and to just know what you're after, right? Because it will help you solve the problems in the end, right? So you just need to know, when you need a line, you just need a point and direction. Don't let them confuse you. They'll throw a lot of information at you, but it's just to confuse you. Don't fall for it. So, let's actually do a couple examples. Of course, I'm going to do the easy ones and then give you the hard ones for homework. problems? Yeah, let's do these and then we'll talk about those and then maybe we'll talk about a few more examples. And tomorrow we're going to have a lot of fun drawing surfaces. Okay, what's the equation of the plane through the point 1, 2, 3? Normal vector minus 1, 7, 4. Yeah.
Minus x plus 7y.
Minus x plus,
I mean, I did the one
No.
equation and then
That was it. That's what I got. Minus x plus 7y.
plus 4
Z.
is equal to 4z is equal to 25.
oh, I guess that's right. But we got that from setting this up first, right? This is the ABC, right? And this was the x naught, y naught, z naught. And so we have minus 1 x
Minus
plus 7 times y minus 2
Plus 4.
plus 4 times z minus 3 equals 0. And you can leave it like that. I actually don't care to simplify it. But yeah, I guess if you simplify, you would have this. You said 25?
Yes.
Yeah. But I'm actually okay with you leaving it here.
Okay.
How do you find the equation of the plane containing those 3 points?
First you have to find the normal vector.
First you have to find the normal vector, right? Because for a plane, well, I erased it. For a plane, we need a point and the normal vector. We have 3 points. We have more than enough points to choose from, so all we're missing is the normal vector. How do we find the normal vector?
Create two vectors and take the cross product.
Yeah, it's actually like the homework problem that we had earlier today that someone asked about, right? There are these 3 points here. 1, 2, 3, there's 3, 2, 1, and then there's minus 1, minus 2, 2. Just connect them and find the normal by taking the cross product. Right? It's one of the more important uses of the cross product is to help us in finding the equation of planes. So
That comes to -8, -10, -8.
let me call this A, B, and that's N. So A would be 2, 0,
2.
minus 2.
-4, -4, 1.
B would be -1 minus 1, -2 minus 2, 2 minus 3. Right. We're going to take their cross product. So block out these two, 0, minus 8. Block out the middle one, minus 2, minus 4. And then you get positive 6 because you change the sign. Block out the last two, minus 8, minus 0. Right? And that's actually equal to n. In fact, I could take n to be anything parallel. So if the numbers are big, that's no problem. We could divide everyone by 2 or minus 2. Get minus 4, 3, minus 4. We could also use that, right? Because when we plug it into the equation, we can divide through by 2 anyway. So this implies the plane is, if I take 1, 2, 3 as the point, I can take any one of those as the point. Then I'd have minus 4 times x minus 1 plus 3 times y minus 2 minus 4 times z minus 3 equals 0. Questions? Some important facts to think about when you're going to be working with
I
word
have a
problems. Yes.
Do you have to use 1, 2, 3? Or can you use
No,
any one?
any one will work. Any one of these please. Right? And if you pick any one of these points and then you actually did this further step of simplifying, they'd all simplify to the same thing. Really neat how that works out. Very important concepts that you should, again, they might look simple when you're writing on the board, but it pays to actually be firm on the basics and make sure you read these and know them like in the depth of your soul so that no one can confuse you, right? Two planes are parallel or orthogonal if their normal vectors are parallel or orthogonal, right? Just like with lines, we can tell if they're parallel by just looking at their direction vectors, right? Everything that has to do with parallel or orthogonal, the vectors are what we look at because they give us the direction, right? The angle between planes is considered to be the angle between their normal vectors, right? Another thing that's very important, anything orthogonal to a plane is automatically parallel to its normal, right? And vice versa. If you're parallel to the plane, you're orthogonal to the normal. Right? We also have a distance formula. I didn't really derive this because we actually did a homework problem that's very similar to this, where we found the distance from a point to a line. To find the point to a plane is very similar. You sort of set up this triangle and do the scalar projection and all that. And you can actually derive, simplify it to get to that. So that's just the distance formula. Did I give an example of that? Find the distance from 284 to that plane. Should I do it? We'll do it, and then maybe we'll just discuss some other problems briefly. Again, sometimes they might say to the plane this, but if, of course, they don't tell you it's a plane, you should be able to recognize it. Ultimately, we're going to need to know how to recognize these things just from the formula. The same way you can recognize a parabola or a straight line just from their formulas. We're going to need to be that good here eventually. So, how do you do this? This is from that point to that plane.
Could we just take from a point on the plane to the point there and find the distance with the distance formula?
Well, you can't just do like any random point. No. Because distance, remember, it's always measured perpendicularly. I actually gave you the formulas there. Just want to plug in. So in this case, we have x1, y1, z1 is actually the point 284. What is A, B, C, and D?
2, 1.
2, 1, 1. What's D?
-5.
D is -5, right? Because over here the D was on that side. Right? So now we just plug in the formula. It's A times x1, 2 times 2, plus B times y1, 1 times 8, plus C times z1, 1 times 4, plus B, which is -5. All that divided by the radical of a squared plus b squared plus c squared. 4 plus 1 plus 1. Okay, that's 16 minus 5. That's 11 over radical 6. What's your distance? And that actually does it for 10.5. So the homework for that is due tomorrow. We only have a couple more minutes. Let's brainstorm a little. What if I asked you to find the equation of a plane that contains a line and a point? How would you do it?
Find the normal vector first.
How?
Using cross
Cross product of what?
two vectors.
Use what point?
Can we just find point from the line, from the equation of the line, and then find the normal vector with the 2 points?
How would you do it with
Are,
a point?
wait, you're given a plane and you just.
I know the plane has a line in it and a point in it, right?
Well,
So
you can choose.
here's my plane. I know it contains a line and some random point. How do I find the equation of that?
Zero vector. So whatever vector you give, you just draw a line, connect it, make another vector, it would be a polynomial.
Connect it with, connect what?
So let's say the vector is 1, 2, 3, right?
For the line?
Right.
Okay, sure. All right, so this is vector 1, 2, 3. That gives you the direction though. Okay.
Right. So essentially a point on that vector would essentially be 1, 2, 3. So if you connect the point with the point on the plane, you get another vector, and then you could just go cross product.
Not really. The point wouldn't be the 1, 2, 3. The point is the x naught, y naught, z naught. That's the v. You could find a point on the line, sure, right? Plug in, say, t equals 0 or whatever parameter you want, and you can actually find a point here. In general, it won't be equal to the direction. And then you make a vector using those 2 points, and you already know that vector, so you can cross product to get the normal, right? And since the line is in the plane, that point you could use for the x naught, y naught, z naught in the equation of the plane. Okay. What if I asked you to find the equation of a plane that contains 2 parallel non-intersecting lines? How would you do that?
We find 2 points on the 2 lines.
So here's my plane, 2 parallel lines. What do you want to do?
We could find 2 points on the 2 different lines.
Okay, so I found this point and I found that point.
Draw a vector from one of them,
And then what?
and you have the other one that you could use one of the lines as another vector.
Yeah, just use direction vector for any one of the lines, which I'd give you the equations, you'd actually know it. Then from that you can find a normal vector. So remember, at the end of the day, you're really saying, okay, I need a point and a normal, right? So you're just figuring out how do you get each of these, right? If I give you the equation of the line, find the point is easy, just plug in a parameter. Finding the normal vector, that's where you have to realize, okay, how do you do it? What if I asked you to find the equation of the line of intersection of 2 planes? Say it again. Equation of the line of intersection of 2 planes.
You set the 2 planes equal to each other.
That's going to be hard to do. Two planes come across each other, they cut. I want the equation of this line.
So we find the intersection points of the 2 planes.
How?
Take the lines and set them both equal.
Set them equal.
Take what? How do you set them equal?
Take the individual components and set them equal.
The equation of the 2 planes.
The equation of the
set
2
them
planes.
equal to each other.
So let's say one plane was x plus y plus z equals 2. The other plane was 2x minus 3y plus 4z equals 6.
X plus y plus z minus 2 equals 2x minus 3y plus 4z minus 6.
Oh, wait, but there's a problem.
Oh, the
X,
problem
Y,
is-
Z.
That's not, actually, wait, I'm not sure. It might be more than one solution.
You can,
Well, couldn't you set one of the
Well, it's
variables?
definitely more than one solution. There's a whole line here. You can solve for any one. There's an infinite number of solutions. Yeah.
If you get
I
two-
just want one.
If you get two equations, can you set one of the variables to 0 and then solve for one of the other two variables?
If
Put that in.
we have
Because
this-
if we
yeah.
set z equal to 0, then we'll have x plus y equals 2, that form for each equation. And then we'll have two equations and two variables, and we can.
Yeah,
solve
you
for
can do that.
difference.
So the theory would be that if you let the line extend long enough, eventually it's going to hit one of the coordinate planes, right? Right? Or we could say, figure out where does it hit the xy plane, so we can plug in the z equals 0 and then solve for x and y, right? So that would be a point on the line, right? The z component would be 0, and these would be whatever you solve for in those two equations that result. How do we get the direction then? So we have the point down. How do we get the direction of the line?
So the direction vector is going to be, it lies in both planes, and so it's perpendicular to both, both normal vectors. You can sort of do the opposite of what we've been doing and take the cross product of the normal vectors.
Right. So the line is in both planes, which means it's parallel to both planes. So by what I wrote over here that I erased, anything that's parallel to a plane is orthogonal to its normal vector. In other words, that line, the line of intersection, is orthogonal to both normal vectors at the same time. Well, how do you find a direction that's orthogonal to both two directions? Cross product. Right? So that to find the direction of that line, you'd actually need to cross product the normals. One way to tackle a problem like that. Let's see what other sort of situation is. All right, so you can see how the situations can sort of get muddled. It's not just, oh, here's a point and here's a direction. That's not how it's going to be. They're going to describe, oh, these two things are crashing into each other. You know, what's the equation of this? You know, that's how they're going to present it to you. But you're going to have to know, okay, all I need is a point and a direction. Calm down. It's not the end of the world, right? You try to draw a picture, oh, that's so confusing. No, just calm down. Okay, I just need a point and a direction. Right? And for a plane, you need a normal direction. So all you're trying to do is figure out how to get to a normal vector. Usually it will involve cross products. Sometimes not, but usually it will. Right? And so that's the idea. With that, I go forth and do homework.